Hello everyone, welcome back. So first thing we're going to do is to summarize what we learned last time. We started from this equation. Work is equal to integral P dV. And starting from V1 to V2. W is work, P is pressure, V is volume. Lower limit V1 is initial volume, upper limit V2 is final volume. This is the most fundamental equation we can use to calculate expansion or compression work. Doesn't matter which one, it works for both of them. Okay, starting from this fundamental equation, we analyze this equation in two different ways. The first method we analyze this equation is the graphic way, graphic analysis. So for example, if you have a diagram where the y coordinate is pressure and the x coordinate is volume, and then you have a curve such as this one, starting from 1 to 2. Pressure goes down from 1 to 2, while volume goes up from 1 to 2. So this is obviously an expansion process. And on this diagram, we say the area under the diagram represents work. Area under 1 to 2 is equal to the absolute value of work. This is what we concluded last time. The reason why we have to add absolute value to work is because work can be positive or negative, but area is always positive, so we add absolute sign to work to make it always positive. The good thing about this method is we can visualize where work is. That's the area under the curve. The downside of this analysis method is we can not really calculate the value of work, because how do you calculate the area under 1 to 2? It's irregular. It's really impossible for us to calculate. So that's why we have another method, analytical. Analytical analysis. That's to say, we start from this equation, integral P dV from V1 to V2, and we also tell you the equation for this curve 1 to 2 is PVN equal to constant, where P is pressure, V is volume, and N is the index, which depends on what kind of gas you have. It's a material property. So we combine those two equations together, and then our conclusion is work is equal to P1 V1 N V2 1 minus N minus P1 V1 divided by 1 minus N, or P2 V2 minus P1 V1 divided by 1 minus N. Both the equations are correct. Sometimes we choose option number 1, sometimes we choose option number 2, but usually we choose option number 1. Why is that? Because we said last time, in equation number 1, you only have to find 4 unknowns. They are P1, V1, V2, and N. However, if you choose the second option, you have to find unknowns. They are P2, V2, P1, V1, and N. So even though option number 1 looks longer, it's actually easier to use. Okay, so they have the same restriction. Your index N cannot be equal to 1, otherwise your denominator will be 0. Okay, so this is what we learned last week, and we just summarized it. And then to better help you understand those two methods, we're going to do one example. Okay, the first example is we have a gas. in a piston cylinder assembly. And it undergoes an expansion process for which PV with the index of 1.5 equal to constant. So what does that mean? That means the n, the index n for this example is 1.5. Okay, the index n for this problem is 1.5. All right, and then we also let you know the initial pressure is 3 bar. Initial volume is zero point 0.1 cubic meter. And then the final volume is zero point 0.2 cubic meter. Has to be bigger than initial because it is an expansion process. Okay, so now we can say this pressure must be 3 bar. We can call it P1. We use 1 for initial and 2 for final. So zero point 0.1 cubic meter must be V1 initial volume, and final volume must be V2. All right, and then what we want to find is work of the process. Right? As an engineer, you want to quantify how much work you can get out of this expansion process, so you know how much work you can use to drive your car. Okay, so now how do we solve this equation? We can go back to our equations. All right, so here, this is the equation we developed last week, which we can use for this example. Okay, so next question is which one you want to choose, option number 1 or option number 2? Option number 1 is longer, so let's take a look. P1, do we have P1? Yes, given. Do we have V1? Yes, given. Do we have V2? Given. Do we have an index n? Yes, index n is given 1.5. So we have all 4 unknowns if we choose option number 1. That means we just need to do plug and chug, and then we can find a solution to work. If we choose option number 2, do we have P2? No, we don't. V2, yes. P1, yes. V1, yes. Index n, yes. So if you choose option number 2, even though it's shorter, but it's more complicated to use because before you use this equation, you have to find P2 first. So now the best way to do it is to choose option number 1, even though option number 1 is longer. Okay, so what is left is plug and chug. So plugging P1 is 3 bars, so make sure you always use SI unit. And a bar is not the SI unit for pressure. Pascal is the SI unit for pressure. So how do we convert bar to Pascal? Do you remember that? 1 bar is equal to 10 to the 5th Pascal. So 3 times 10 to the 5th Pascal multiplied by V1. V1 is zero point 0.1 cubic meter. And n, the index n, what is index n? It's given. It's 1.5. So index 1.5 multiplied by V2. V2 is given 0.2 cubic meter. And then again, index 1 minus 1.5 minus P1 V1. Okay, let's do it again. P1 is 3 bar and convert bar to Pascal by multiplying 10 to the 5th. Multiplied by V1, which is given 0.1 cubic meter SI unit already, divided by 1 minus n, and n is 1.5 given. Okay, so now what you can do is just use your calculator. Your solution will be 17,000 573.59. And what is the unit to my solution? If you use SI unit for every parameter in your calculation, your solution will also have SI unit. What is the SI unit for work? It's joule. Okay, and then one more step. Usually for engineers, we use another unit. What is that? Kilojoules, because joule is too small. So one more step to convert joules to kilojoules. That is 17.6 kilojoules. Okay, so that is my solution. And now, let me tell you this. You notice that your solution is positive. Do you remember what the positive work means? If work is greater than zero, what does that mean? System generates work. If your solution work is negative, what does it mean? System consumes work. This is an expansion process, so the gas will push the piston up, generating work so you can drive your car. So that's why your solution must be positive. Okay, so that's the example. Okay, and next one, we're gonna expand your knowledge about total energy, broadening our understanding of energy. Okay, like we said before, total energy is written as capital E. Capital E is for total energy. Total energy has three components. They are kinetic energy, potential energy, and internal energy. Internal energy is something new we learned in this class. In addition to kinetic energy and potential energy, which you learned in high school or college physics before coming to this class, is internal energy. The three of them together is the actual total energy. Internal energy is usually represented by the temperature of the object. Usually, the higher the temperature is, the more internal energy you have. Okay, so capital U represents internal energy. And the unit is still the same for any other energy, it's joule. And then we introduce lowercase u. Lowercase u is equal to capital U over mass. It's called specific internal energy. And again, the SI unit will be joules per kilogram. And next one, we talk about energy transfer by heat. Energy transfer by heat. Okay, a very common way for us to transfer energy is by heat. Heat transfer. Okay, the first thing we need to know about heat transfer is it has a direction. Heat is only transferred from high temperature to low temperature without any input. Okay, so there are two things to remember. First one, heat is always transferred from high temperature to low temperature. This one is really easy to understand because it is our daily life experience. Everybody knows that. Okay, so for example, you have some really hot water, and if you just leave it there for a while, what's gonna happen? It's gonna cool down to room temperature because heat is transferred from the hot water to the cold environment. Okay, the second thing we want to remember is the condition. What is the condition? Without any input. That means if you don't do anything, if you just let things happen naturally, heat must transfer from high temperature to low temperature. But you can reverse this process. For example, your AC or your refrigerator, what they do is to transfer heat from low temperature to high temperature. But in order for this to happen, what do you have to do? You have to pay electricity. You have to pay energy. You have to input energy to make this process happen. Okay, so regarding heat transfer direction, we have to remember two things. First one happens from high temperature to low temperature. Second one, if you don't do anything, if you just let it happen naturally. Okay, all right. And then the second one is the sign conventions. Just like work, we also have positive heat transfer and also negative heat transfer. Okay, if your heat transfer is positive, we use Q for heat transfer. If the solution is positive, that means your system gains heat. However, if your heat transfer is negative, that means your system loses heat. Okay, and your textbook may say rejects heat. Okay, and then just like work, we also have something similar, rate of heat transfer. Rate of heat transfer. Rate, that means what? Heat transfer per unit time. So heat transfer divided by time. And then the syntax we use is Q with a dot on top of it. It's heat transfer rate. So what is the unit for Q dot heat transfer rate? It's going to be joules divided by seconds, which is equal to watts. Okay, so the unit for heat transfer rate Q dot is watts. All right, so if we rewrite this equation, we can move Q to the left-hand side and everything else to the other side. This becomes Q dot multiplied by T. Do you remember we have such an equation as W equals W dot times T, where W dot is power? And this equation is true only when W dot is constant. Because if W dot is constant, you can just plug in W dot as a constant. However, if W dot is not constant over time, if W dot, the power changes over time, what do? We change the multiplication into integration, T1 to T2. And same thing happens for heat transfer. If Q dot, which is heat transfer rate, not a constant, what you do is the same. You change multiplication into integration. So it becomes Q dot times dt from T1 to T2. Okay? And then if there's no heat transfer, no heat transfer, then heat transfer must be equal to zero. And we call it, it has a name, adiabatic. If you see the word adiabatic, that means heat transfer is equal to zero.